So now we're going to talk about the aldol condensation, which is the reaction of two equivalents of an aldehyde, in this case acetaldehyde, which go to give an alpha-beta unsaturated aldehyde. We're doing this under basic conditions such as sodium hydroxide. So sodium hydroxide is soluble. We have a sodium anion and a hydroxide counterion, and the product, or the byproduct that we give off, is an equivalent of water. The first step of the aldol condensation under basic conditions is taking our hydroxide and making an enolate, so deprotonation of the proton alpha to the carbonyl. And so the reason we can do this with sodium hydroxide is because the formed enolate is resonance stabilized, and so we can have the oxygen atom negatively charged in this case. So what we've done by deprotonating the carbon atom is making a good nucleophile. We can then have another equivalent of aldehyde come in, and we can take the negative charge when it's on the carbon and attack the carbon of the carbonyl, kicking the electrons up onto the oxygen. And so we have our initial aldehyde unit here, and it's now attached to the carbon of the carbonyl, and we have the oxygen atom negatively charged. So in this case we have no resonance stabilization. We can then have a water molecule, which we made in this initial step, come back, and we protonate the alkoxide to give us an alcohol. And this will sit, but if we give it a little bit of heat, we can again use a hydroxide anion to deprotonate alpha to the carbonyl. We still have our hydroxide here, and this is resonance stabilized, where we have the negative charge on the alcohol. Excuse me, on the oxygen atom. And so, if we want to get to our product, instead of looking at this resonance stabilization, we can have the negative charge on the carbon come down and kick out the hydroxide. And so in this case we give off an hydroxide, which we used here, and we are getting the alpha-beta unsaturated aldehyde from the reaction of two equivalents of an aldehyde in a basic environment.